Hi everyone, I'm Joey Carlson. I'm with the Department of Electrical and Computer Engineering at UC San Diego, and today I'll be presenting some of our recently published work in Transactions on Wireless Communications titled Hierarchical Codebook Design with Dynamic Metasurface Antennas for Energy Efficient Arrays. So we'll first start and talk a little bit about the motivation behind this work. So for next generation wireless systems with massive MIMO or millimeter wave or terahertz communications, we're really looking to scale up the number of antennas in our array to just create very, very large antenna arrays. However, with the scaling of the number of antennas, naturally for analog or hybrid or digital precoding, will also cause the hardware and components to scale as well. And so here we've shown an analog precoding architecture with phase shifters connected to this very, very large antenna array. And now as expected for many antenna elements, we will require many, many phase shifters, many power amplifiers. All of these components will scale with the number of antenna elements, which means more power consumption, more cost, and greater hardware footprint. And so we're looking for sort of a workaround to this. How can we scale these antenna arrays without also scaling the power consumption and hardware footprint? So one of the proposed solutions to this is to use something like reconfigurable antennas, or in this case, dynamic metasurface antennas, to scale these large antenna arrays. So dynamic metasurface antennas are a type of slotted waveguide antenna array, and they they enable beamforming via reconfigurable components attached to each element. So here we have a waveguide as sort of the base and physical structure of our DMA, and these resonant DMA elements with this special geometry are etched into the waveguide to radiate out power through each of the different slots. Now the key thing to reconfigurable antennas and DMAs here is that there are reconfigurable components integrated into each of these elements, such as fractor diodes or pin diodes, which can change the resonant frequency or other attributes, but here the resonant frequency of the DMA design, and thus enable beamforming. And these reconfigurable components are often low power. Fractor diodes consume negligible power, and so we can scale up the number of antenna elements in our array without adding on extra power consumption to enable beamforming. And so that is really the key solution that DMAs solve for antenna arrays. Now, in our work, what we wanted to do is look towards some improvements on the current DMA beamforming design. And so while DMAs have these great benefits in terms of power consumption savings and hardware footprint savings, naturally there's going to be some challenges and limitations and trade-offs for the DMA compared to a typical phased array architecture. And one of the main limitations is the available beamforming weights. And so as we see on the figure on the right, for a desired weight, which is a unit amplitude, 360-degree phase range, which is something that we might be able to achieve with a phased array, DMAs have a weight distribution dictated by that red curve there, which is called the Lorentzian constrained distribution. So we have a limited phase range. It goes from 0 to negative 180 degrees, and it has that variable amplitude curve. So we have this tied phase and amplitude curve that we must use for the different DMA weights on our antenna, which naturally is going to lead to some beamforming degradation, maybe some steering error compared to a phased array. So now one simple way to beamform with the DMA though, is simply to map your desired solution, so your unit amplitude phased array solution, onto that Lorentzian constraint distribution. Now in our paper, we wanted to make two key improvements to these DMA beamforming methods. One, we wanted to improve this mapping approach where we map the desired weights onto the DMA weights by applying a common phase rotation to the desired weights, the unit amplitude weights, prior to mapping, so that we then get a new set of mapped DMA weights that still steer a beam pattern in the same direction, but perhaps has higher beamforming gain or better steering accuracy. And then the other improvement that we wanted to make is to leverage that zero weight in the middle of the Lorentzian constraint distribution, as you see in that figure, the zero weight, to enable a hierarchical codebook. Since creating broad and narrow beams often requires turning on or off certain elements, we figured that leveraging that zero weight could allow us to steer some broad patterns And then we should be able to steer some narrow beam patterns by having all elements active. So here we're showing some results for this hierarchical codebook based on a DMA that was designed in HFSS. And so these are real beam patterns from a design DMA that we created in HFSS. And so on the figure on the left for layer 2, where we only have 2 code words, we see that by leveraging that 0 weight and turning off many elements, that we can create 2 very large and broad beam patterns to cover the different angular range, to cover approximately 120-degree angular range with our dynamic metasurface antenna. So our proposed hierarchical codebook design to create broad beam patterns with the 0 weight is successful. Moreover, for layer 4 of the hierarchical codebook design, so with 8 beam patterns, we find that we are able to steer much narrower beams there. So we have 8 code words there in that layer 4. So we're still able to create very narrow beams by turning on all the different elements and configuring them with our Lorentzian constrained DMA weight distribution. And then we are also comparing these results to something like a phased array with a patch antenna that was also designed in HFSS to ensure consistency. And so we see there that the steering angle for that last hierarchical codebook layer with 8 different beam patterns, the steering accuracy is consistent between the phased array and DMA. So both the phased array and DMA are able to accurately steer a beam in a desired direction. And now lastly, we show some results for spectral and energy efficiency between the DMA and a phased array for comparison and using this hierarchical codebook design. These results are done using Quadriga as the channel simulation software, and then also incorporating our HFSS beam pattern results so that we can be as realistic as possible with these spectral and energy efficiency results. We also calculated power consumption for all 3 different cases based on a power consumption model. First, on the table on the right, we list a couple of the trade-offs between the DMA, active phased array, and passive phased array. So for the DMA, naturally the power consumption and component loss will be low because there's fewer components, the varactors consume negligible power, but the beamforming gain will be lower than the phased array due to the Lorentzian constraint. The active phased array with the patch antenna means we are using active phase shifters, which consume power but have lower component loss compared to passive phase shifters. So naturally the power consumption will high, the component loss with power dividers and the active phase shifters will be perhaps medium, and the beamforming gain for both this and the passive phased array will be quite high, will be the maximum that we could achieve technically. And then for our passive phased array, naturally the power consumption will be low. We're assuming passive phase shifters in this case, so negligible power consumption. However, passive phase shifters often have a very high component loss, and so this will be high in this case. Now looking at the results, the spectral efficiency shown on the left there, we see that the active phased array has the best spectral efficiency, which is expected. It has the highest power consumption and the highest beamforming gain, so it should perform the best in terms of spectral efficiency. However, the DMA does not fall very far behind it. There's around a 2 dB input power difference between the DMA and the active phased array. And then because of the high component loss of the passive phased array, this is by far the worst case. That component loss allows for much less input power, or less power transferred to the antennas for the beamforming gain. And so we get a much lower power transfer from the transmit to the receive antenna for this case, so we have a much lower spectral efficiency. Now when we compare the energy efficiency, we actually find that the DMA performs nearly twice as well as the active phased array. So there's around a 2x difference there, and that's just because the active phased array uses active phase shifter, so there's larger power consumption there, whereas the DMA has these varactors, and so there's very low power consumption. So we actually find that the DMA performs the best compared to the active phased array, while only maintaining a small performance gap in terms of spectral efficiency as well. So thank you so much for listening to my talk, and for more information, please refer to the full paper. Thank you.